Tonight, you look up and see a single point of light. It looks calm, it looks distant, it looks like it could never touch you. But somewhere out there, spinning 700 times a second, sits an object so dense that 1 teaspoon of it would outweigh every car on Earth combined. You are about to fall into it. Are you ready? Let's set the scene. You are floating in space, 1,000,000 kilometers away from a neutron star. From here, it looks small, harmless, a tiny glowing marble against the black, but looks, out here, are the universe's oldest lie. This marble used to be a star 20 times heavier than your sun. It collapsed. It died. And what's left behind is not a star anymore. It is a corpse the size of a city, spinning faster than a kitchen blender, packing the mass of an entire sun into a sphere you could walk across in an afternoon. You begin to fall. At first, nothing feels wrong. Space is empty, silent. You drift, weightless, watching the marble grow slowly brighter. Your instruments tell you it has a magnetic field 1,000,000,000,000 times stronger than Earth's. 1,000,000,000,000. If you had a credit card in your pocket right now, at this distance it would already be ripped from your body and flung into space at nearly the speed of light. You don't have a credit card. You have something worse. You have atoms, and atoms respond to magnetic fields too. Keep falling. 10,000 kilometers out, something changes. You feel a pull, not the gentle tug of Earth's gravity that lets you jump and land softly. This is different. Sharper, one-sided. Astronomers call this spaghettification, and the name is almost funny until you understand what it means. Gravity does not treat your whole body equally. Your feet, closer to the neutron star, are pulled harder than your head. The difference is small on Earth. Here, it is catastrophic. You are being stretched, millimeter by millimeter, into a thread. Stephen Hawking spent his life studying exactly this kind of extreme gravity, the places where Einstein's equations stop behaving politely and start describing horror. He once said, "The universe doesn't care about our comfort." Falling toward a neutron star, you finally understand what he meant. 1,000 kilometers out. The pull is no longer gentle, it is violent. Your body, if it were still a body, would already be a thin strand of matter, longer than a football field, thinner than a hair. Every atom that once made you, is being pulled apart at the seams by a gravitational gradient that no human engineering could ever resist. This is not death by impact. This is death by stretching, atom torn from atom in complete and total silence, because sound cannot travel through the vacuum that surrounds you. Why does this happen? Picture space-time as a flat rubber sheet stretched tight. Now, place a bowling ball in the center. The sheet bends. Roll a marble nearby, and it doesn't move in a straight line anymore. It spirals inward, following the curve. That's gravity, according to Einstein. Not a force reaching out and grabbing you, but the shape of space itself, bent so severely around a neutron star that falling forward and falling down become the exact same motion. There is no escape route because there is no away. Every direction leads inward. Edwin Hubble spent his career proving the universe is far stranger and far larger than anyone believed, that galaxies rush away from each other, that space itself expands. But even he never had to reckon with gravity this extreme. Neutron stars weren't confirmed until decades after his death, discovered through a mysterious ticking radio signal that scientists briefly, jokingly, called LGM-1, Little Green Men, before realizing they'd found something almost as strange as aliens, a dead star, spinning, beaming radiation like a cosmic lighthouse. You are close now. 100 kilometers. The surface below you is not rock, it is not metal. It is a crust of crystallized atomic nuclei, packed so tightly that the laws of ordinary chemistry simply stop applying. Beneath that crust, physicists believe there may be a soup of neutrons so dense it behaves like a liquid, flowing without friction, a state of matter that exists nowhere else in the observable universe. You are about to collide with something that isn't a planet, isn't a star, isn't anything Earth has an analog for. Here's the part that should terrify you most. Even if somehow you survived the stretching, even if you were made of some impossible unbreakable material, the moment you touch the surface, you would be moving at nearly half the speed of light. Not because you're being propelled, because gravity has been accelerating you the entire fall, patiently, silently, for the last several seconds. The impact would release more energy than a large asteroid strike. There is no scenario, no material, no version of you that walks away from this. And yet, strangely, this is not even the most extreme object in the universe. A neutron star is what's left when a massive star dies but doesn't quite have enough mass to become a black hole. It is, in cosmic terms, still holding on. Add just a little more mass, and gravity wins completely. Space-time doesn't just bend anymore, it closes, it seals shut. That's the difference between falling into a neutron star and falling into a black hole. One crushes you against a surface. The other erases the very idea of a surface and of you entirely. Carl Sagan used to remind people that we are made of star stuff, that the calcium in your bones and the iron in your blood were forged in the hearts of stars just like this one, before it died. There is something quietly beautiful in that, and something quietly horrifying too. The same physics that assembled you, atom by atom, over billions of years, is the same physics that would unmake you in a fraction of a second if you fell too close to the wrong kind of star. Why does any of this matter to you, sitting comfortably on Earth tonight? Because it recalibrates what solid ground actually means. You live on a thin, fragile shell of rock, 13,000 kilometers across, orbiting a middle-aged star at a very particular, very lucky distance. Not too close, not too far. You experience gravity so mild you barely think about it, strong enough to keep your coffee in the cup, gentle enough to let a bird fly. Out there, gravity has other settings that don't care about coffee or birds or you. The Voyager probes, launched in 1977, are still out there right now, drifting through interstellar space, carrying a golden record with sounds of Earth, whale song, laughter, a heartbeat, in case anything or anyone ever finds them. They will likely outlive the sun. They will likely outlive Earth itself. And even they, moving faster than any object humans have ever built, would take literally hundreds of thousands of years to reach the nearest neutron star. The universe doesn't just hide its monsters. It hides them behind distances so vast that far away barely means anything anymore. So when you look up tonight and see that calm, steady point of light, remember what calm really means out there. It doesn't mean safe, it means slow, on a timescale you can perceive. Somewhere in this galaxy right now, a neutron star is spinning hundreds of times per second, sweeping a beam of radiation across the cosmos like clockwork, utterly indifferent to whether anything is watching. It has been doing this for millions of years. It will keep doing it for millions more. You are not falling into one tonight. You get to close this and go back to your ordinary, gentle gravity, your ordinary breathable air, your ordinary unstretched body. But somewhere out there, the universe is still running its most extreme experiment over and over, without an audience, without mercy, and without ever once looking away.